Hello, this video is part 5 in a series of videos on classification of linear second order PDEs. So in the previous videos we have part 2, part 3 and part 4. We've done some 6 examples of how to classify a PDE and how to reduce it to its canonical form and how to integrate it from there. Now in this video we're just going to revisit part B of the examples that we did. So in part B we have this PDE here, which we classified it and found that it's parabolic. So if it's parabolic, we could only derive one canonical variable from the characteristic equations y plus 2x. The other one, we said we are free to choose it so long as our choice gives a non-vanishing Jacobian. So in part 2 we chose eta equal to y, and then we showed that the ODE can be reduced into this canonical form u eta equal to 1 over 4 e to the eta. This can be integrate this twice with respect to eta. It gives you this, where f and g are arbitrary functions. And then in terms of the original variables, it looks like this. Then in the last video, we posed the question, well, what if this eta is chosen differently, because we said it can be chosen to be anything. So in this video, we're going to show you two cases of different choices of eta. And we're going to show you that in terms of the canonical structure of the PDE, and indeed the solution in terms of the original variables, the basic structure is still going to be exactly the same. In fact, the canonical form is going to remain invariant. It's going to be exactly the same irrespective of the choices. So in case 1, we are going to choose so case 1, we are going to choose eta to be equal to y minus 2x. So remember, xi is y plus x, so we just chose it to be the same thing with a minus in the x term. So let's see what this gives us. So the first thing we need to do, of course, is to make sure that the Jacobian is non-zero. Okay, so xi x is 2, xi y is 1, eta x is minus 2, eta y is 1. So the Jacobian is going to be equal to 2 times 1 minus negative 2 times 1. It's going to be negative 4. This is non-zero. Okay, so in terms of graphical setup, the Jacobian being non-zero just ensures that the two coordinate systems that you have, or the two variables that you have, do not correspond to parallel lines, if it's straight lines, for instance. Okay, so in this case you can see, we can actually see that these are not going to be parallel, because if you take let's take the etas, for instance, these equal to constants, if C2 is a constant, this is y equals to 2x. So it's just going to be a straight line going through the origin with gradient 2. If C2 is 1, then that is going to shift up. So that means the eta equal to a constant x's are going to look like that. And then if you take C1 to be 0 here, that's going to give us y equals to negative 2x. So in this case, those are going to look like this. And you can see that clearly these are not going to be parallel. So that's going to be a legitimate coordinate system. Right, so let's go to the derivatives. So ux is going to be the x derivative of xi times uxi, and then plus the x derivative of eta times u eta. So it's going to be uxi minus 2u eta. Then from this we can get the xx coordinate. The coefficient of this term is going to be the square of this. And then the coefficient of this term, maybe, let's write this whole thing here, otherwise we're going to run out of space. So we said the coefficient of this is the square of this term. And then the coefficient of this one is going to be 2 times this coefficient times this coefficient. So it's going to be minus 8. This one is going to be the square of this one. So it's going to be 4. Since these are constants, there is not going to be terms here. Then uy is going to be this term times uxi plus this term times u eta. So that is going to be simply uxi plus u eta. That means uyy is going to be u xi plus 2 uxi eta plus u eta. And then the mixed derivative term. So the first term is the coefficient is simply going to be this coefficient times that coefficient. So it's going to be 2 xi. Then the mixed derivative coefficient is we cross multiply these and add. So we've got 2 times 1 plus negative 2 times 1. They add up to 0, so the mixed derivative term is going to be 0. Then the last term, we simply multiply those two. So that is going to be minus 2 u eta. Okay, so then we can substitute into the PDE. So the PDE becomes, so the first term is uxx, so it's going to be 4u xi minus 8u xi eta plus 4u eta. Take away 4 into 2u xi minus 2u eta, and then plus 4 into u xi plus 2 u xi eta plus u eta equal e to the y. Let's just write it like that for now. Then we simplify. So the xi terms, there is 4 here minus 8 plus 4. So 4 plus 4 is 8 minus 8. So these cancel out. the xi eta terms, there's minus 8 here and plus 8 here, so they cancel out again. And then the eta terms, there is 4 here plus 8 plus 4, so it's going to give us 16. So we have got 16 u eta equal to e to the y. Now we need to express everything in terms of the canonical variables here. So we have got xi equals to y plus 2x eta equals y minus 2x. Can we eliminate x here? Yes, we can. Xi plus eta is 2y, so that means y is xi plus eta over 2. So it means our canonical form is going to be u xi equal 1 over 16 e to the power xi plus eta all over 2. So this is our canonical form this time, okay, which is to be compared with this one that we got before. Okay, now can we integrate this? Yes, we can. So let's integrate. So if we integrate this once with respect to eta, that means we are going to have to multiply by 2. So it's going to be 1 over 8 e to the power xi plus eta over 2 plus a function of xi, integrate again, multiply by 2 again, so e to the xi plus eta over 2. This is going to be eta f of xi plus g of xi. And then in terms of the original variables, 1 over 4 xi plus eta over 2 in terms of the current coordinate, canonical coordinates, is just y. Then here we've got y minus 2x times f of y plus 2x plus g of y plus 2x. And so this is our general solution this time, to be compared with this one here. You can see that the first term is exactly the same. So that was case 1. Case 2, we are going to, so this one, we have got no choice with this one. That's what we found from the characteristic ODEs. This one, we have a choice. So usually we advise that you choose this one to be as simple as possible. Okay, so in part 2 of the videos, we chose it to be y. We said it's motivated by the fact that that is just a function of y, but we could choose it this choice we did in case 1 is not exactly the simplest choice that you could let yourself go through, but we were just doing this for purposes of for educational purposes, just to show that it still works out nicely. The other simple choice is just letting eta to be x. In terms of what these coordinates are going to look like, so graphically, if you choose eta to be x, that means your canonical coordinate, the x equal to constant, is just going to be the same as the eta equal to a constant. So it's going to be eta equals to 0, eta equals to 1. This one we've already shown that it's it's going to be lines which have got a -2 gradient going across like this. And as you can see, these are not parallel, so we would expect that the Jacobian is not going to be equal to 0, but we have to work it out. So that's what we're going to do. So eta x is 1, eta y is 0. Then the Jacobian is just the sum of the cross multiplication thing that you get here. So 2 times 0 is 0, then 1 times -1, so this is 1. So that means that coordinate system is fine. Okay, just one moment. Actually, this is +1, so it's going to be -1. All right, so that means ux is going to be 2 times uxi plus u eta, 1 times u eta. Uxx is going to be 4u plus 4 uxi eta, 4 coming from 2 times 1 times 2, and then plus u eta eta. Then uy, eta does not depend on y, so uy is just going to be uxi, and so uyy going to be uxi xi. Uxy going to be 2u xi xi plus u xi eta. Then if we substitute into the ODE this time, this is the ODE, so we are going to get uxx is 4u xi xi, 4u xi eta, u eta eta minus 4 uxy here, so that is 2u xi xi plus uxi eta, and then uyy is simply uxi xi, so 4u xi xi equals e to the y. If we take the xi terms, there's 4 of them here and 4 of them here, that's 8 minus 8, so this cancel out. The xi eta terms, there's 4 of them here, minus 4, cancel out. So we're just going to have this term here. So we have u eta eta is e to the y. We need to write y in terms of the canonical coordinates. Now notice here that x is just eta, so that means we can write that as 2 eta. So xi is y plus 2 eta. So y is actually xi minus 2 eta. So the canonical form this time is going to be e to the xi minus 2 eta. Let's integrate this. Integrate once with respect to eta, going to be minus 1 over 2 e to the xi minus eta plus a function of xi. Integrate with respect to eta again. This one is now going to be 1 over 4 xi to the power 1 over 4 e to the power xi minus 2 eta this is going to be eta f of xi plus g of xi. Then in terms of the original variables, xi minus 2 eta is just y. So then here eta this time is x, f of y plus 2x, g of y plus 2x, where f and g are arbitrary functions. So you can see that in all cases our final solution is basically the same. There's those slight differences because of the difference in the canonical coordinate, the second one chosen. All right, thank you. Hopefully this has been useful. Again, thanks for watching. You can subscribe to get notified when we post new stuff, especially if this has been useful, right?